Let's take a look at this pesky Dolly problem. I've had a couple of students ask me about this, and I didn't quite have enough time in class the other day to go over this, so let's look at it together. All right, so with a problem like this, right, you're pushing on the safe, and the safe's on the top of a dolly, and these two things are moving together, okay? So it says on a distant planet where the gravitational field strength is 10 newtons per kilogram, a physicist has finally invented a shop dolly with frictionless wheels and is using the dolly to move a large safe full of gold. The safe, including the gold, is 875 kilograms. The mass of the shop dolly, including the wheels, is 5 kilograms. The coefficient of static friction between the safe and the dolly is large enough, mu s is 1.1, that the safe does not slip relative to the dolly. That's important. The physicist pushes on the safe with enough force to cause it to accelerate with a 0.44 meters per second squared acceleration. Okay, so the way you want to tackle a problem like this is, the important piece here is that it says that they're moving together, right? There's enough friction between the dolly and the safe that the safe doesn't slip, right? So you know that the friction between the two things is static, and that's fine, and that's great. The point is that they move together, okay? And anytime something moves together, you can treat that thing as just one object. Essentially, this person is pushing on a frictionless safe dolly and sliding it around on the floor, okay? So that's how we're going to start, okay? We're going to treat them as one thing, okay? So again, I have my picture. Now I'm going to draw my force diagram. There's the dot, and I put the weight of the thing. So, right, you have the weight of the Earth pulling on the system, okay? And then you have a normal force of the floor pushing up on the system. And then the only other thing that's touching this is the person pushing it. So then you have this push force forward, right? And we already know that there's no friction between the dolly and the floor, right? So I don't have to worry about a backwards frictional force. So this is what I have, okay? Now, the mass of the system, and this is where you have to be really careful, right? I'm going to add all the masses together. So I have 880 kilograms as the mass of the system. And what we're really interested in here, the vertical forces are balanced, and that's marvelous, but I don't care about that. I care about the direction of motion. Okay, so in the x direction, in the direction of motion, I know I'm accelerating, so I'm going to use Newton's second law. There it is. The net force equals mass times acceleration, and I'm going to plug in what I know, right? So I've got the push force acting forward. It has to be equal to the mass of the system times the system's acceleration. Okay, so I plug in those numbers, 880 kilograms for the mass of the system, 0.44 as the acceleration of the system, and voila, I know what the push force is, right? 387.2 newtons is the amount of force that it takes to push the system. Okay, all right, great. So what do I do with this? I have the push force that is not the amount of friction that's between the two things, okay? So here's the deal, right? That frictional force, now class, this is the thing. When you're dealing with a problem that has multiple moving objects, and by the way, this is where we're headed, okay? We're going to have multiple things moving together, moving as systems. I started the problem by treating the whole thing as one system, okay? And that's great, and that'll give me some information. But now, that frictional force is inside the system, okay? So in order for me to tease out what it is, I need to draw free body diagrams or force diagrams for the individual things inside the system. Okay, so I'm going to start with just the safe. So if we're looking at only the safe, right, I've got the dot, there's the weight of the Earth on the safe, and there's the normal force of the dolly pushing up on the safe, right, and then the person is pushing forward on the safe. Okay, now let's say you stopped there and said, okay, those are the only forces acting on it, and if you tried to find well, we know what F is, right? We found out F over here is 387.2 newtons. If you use this force right here, and then the mass of the safe, right? If you go, okay, well, that force, F equals ma, right? If that's the only force, so I'm going to divide this by the mass of the safe. You're going to get an acceleration that's bigger than the acceleration of the system, okay? So we know that there must be some other force opposing that's pushing backwards on the safe, and that's the static friction that's acting between the safe and the dolly, right? All right, one way to think about this is that the the friction between the safe and the dolly is pushing the safe backwards, but the dolly forwards, right? If you look at the dolly, the only thing that can be moving the dolly forward, because we're not directly pushing on the dolly, we're pushing on the safe, it must be a frictional force pushing on the dolly forwards. So if it's pushing the dolly forwards, it has to be pushing the safe backwards, and that's good. Because now when in the direction of motion, right, I've got the push force forward, I've got minus the frictional force equals the mass of now just the safe, because I'm looking only at the safe, times the safe's acceleration. I can plug in my numbers. Here's the push force that I found over here. See, that's the same. Minus the frictional force, that's what I'm looking for, equals the mass of just the safe now, times the safe's acceleration. Now, why am I using the same acceleration as I did for the system? Well, because it's in the system, and everything in the system is moving with the exact same acceleration. That's when you're dealing with system problems, everything in the system has the same acceleration, different masses. But as a system, you can treat it as one mass that has the same acceleration. I mean, there's a lot of things going on here, but you do the algebra, you multiply these together, you subtract this over, multiply the minus sign over, right? And you end up with 2.2 newtons of frictional force. You're like, okay, sweet, I'm done. Well, yeah, we could be done, or we can check it, right? Let's look at now, these diagrams are not scaled relative to each other. None of them are. My apologies for that. But anyways, so if I look at the dolly, right, if I draw a force diagram for the dolly, right, there's the dolly, and now here's the weight of the earth pulling down on the dolly, okay, and now I have the normal force of the floor pushing up. Now that's huge. You're like, why is that so big? Those aren't in balance. Well, because the safe is pushing down on the dolly, and the normal force of the safe pushing down on the dolly plus the weight of the earth pushing down on the dolly is being balanced by the normal force of the floor pushing up on the dolly. Okay, that's really cool. Love that. By the way, so here's this is the normal. Let's see. This is the normal force of the safe on the dolly, and this is the normal force. Oh, I don't have that over here. But I do have it here. So this normal force of the safe on the dolly, normal force of the dolly on the safe, those are third law pairs, opposite direction. Now, they should be equal in magnitude, but these aren't scaled to each other, but just pretend that they are. Okay, so I've got the vertical forces taken care of. Now, what's going on horizontally? What's the only thing touching the dolly? There's no friction from this surface right down here, but there is friction from that surface, and that's the frictional force that's pushing forward on the dolly. So now I have that. So again, in the direction of motion, I'm going to use my Newton's second law equations here. So the friction is equal to now just the mass of the dolly times the dolly's acceleration. So 5 kilograms times 0.44 meters per second squared. And look what I get, 2.2 newtons of frictional force, right? We already know that the frictional force pushing the dolly forward and holding the safe back, that's a Newton's third law pair. So they had better have come out to be the same number, right? This is a way that I can check my work to see if I'm thinking about this correctly. But anyways, I know that was really fast. You can go back through and watch this and think about it over and over again if you like. But the deal is, and we're going to be playing with this more in class, of systems of masses moving together. But the way you deal with a system is in almost every case, you're going to start by treating it as one big system where you have just one big mass that's all moving with the same acceleration, and you can find some forces. Or sometimes you're given some of the external forces on the system and you find the system's acceleration, and then you take that into the pieces, right? I've drawn a force diagram for each piece of the system, and those are totally different. But the cool thing about the system is that inside the system are all these Newton's third law pairs, right? This one here, and this one here, and this one here, and this one here. And those are going to give you information inside the system. Okay, we'll talk more about this in class. I hope this helps. I'll see you next week.